Graphs, a collection of vertices connected by edges. All computer scientists are familiar with graphs and know that from this simple structure, a variety of complex mathematically based problems emerge. After adding weights or capacities to the edges, as well as orientations, we dive deeper into the entanglements of graph theory. A famous question that comes from this is the max-flow min-cut problem. One vertex will be the source of the flow and the other will be the sink for it. Let's pose two questions. Number one, how can we cut the graph into two distinct parts such that the sum of the edges capacities that we cut is the least? And what is the greatest amount of flow that we can push from the sink to the source, not exceeding the capacity of any edge? It turns out the value that we get by answering these questions is the same. Now, this max flow is very desirable, and I'll explain why later. Let's play a game. You give me a cut, and I'll give you a better cut. A better cut being one where the sum of our capacities is smaller. If we repeat this process enough times, eventually we will get the minimum cut. This is how our algorithm uses the computer to improve and ultimately find the min cut. We can use the min cut to find the max flow, since these are two interchangeable values. My part of this algorithm is returning the head and tail of every path from the source to the sink, as well as its flow. As with any algorithm, there is a complexity constraint. Initially, we started with O of nm squared time in the worst case. In order to reduce the time complexity, the operations on our graph had to be done in O log n time. To achieve this, we used the data structure dynamic trees. The original paper by Daniel Sleator and Robert Tarjan defines a dynamic tree to be a collection of vertex disjoint trees under a sequence of operations that links two trees by creating an edge between them and one that splits a tree in two by deleting an edge. The four advantages cited by this paper are computing nearest ancestors, solving network flow problems, computing certain kinds of constrained minimum spanning trees, as well as implementing the network simplex algorithm for minimum cost flows. In particular, the dynamic tree is used to represent a set of vertex disjoint paths. To represent this, we can convert some edges to dashed and keep some as solid. This is called the naive partitioning. Namely, the edges connecting different paths will be dashed. As described in a write-up about our project by a member of our research group, one of the specific advantages of a dynamic tree is that when traversing back to the root, we do not cross many paths. This means that both finding the root of a tree containing a particular vertex or updating the cost from a particular vertex to the root. Right now, the naive implementation was programmed by a member of our group. But one of the problems is that some operations like finding the root and averting the tree take a linear time in the worst case. Tarjan actually proposes a variation where avert is not even used. There is quite a lot of literature to cover on the topic of flows, and even about dynamic trees, and one of the advantages of working on this problem in a group is that the members of the group made sure that everyone is on the same page in terms of understanding the concepts. This is particularly useful when exploring a novel or difficult topic, although in this case graph theory is not really something new. Now for some practical uses of maximum flow. One example is airline or public transportation scheduling. What would be the maximum number of airplanes or trains that we could efficiently use at a certain time, given that there are constraints on how many buses can be on the same road or planes in the air? A classic example of max flow are pipes and water. Finally, doing computer science for the sake of computer science, learning more about graphs are all viable pursuits. Thank you for watching.